Well, welcome to everybody to the October 7th United States Data Science Workshop. I see an interesting question here. I want to spend just a second on notable. I think it's notable and worth mentioning, in other words. And let me just comment that there's two components of it. Notable itself is a nice programming notebook, an IDE, an integrated development environment. It's like a Jupyter notebook or Google Colab, except it does two extra things. One, it has Excel-like functions that are useful. And number two, you can either manually create visualizations or it'll automatically do it for you. Most notebooks don't do anything except you write your code, and you can use markdown language so you can say what the code means, but there are no bells and whistles. This comes with bells and whistles. And what I'll report this Tuesday at the Medical Intelligence Society meeting is the second aspect is really interesting. It's integrated with ChatGPT as a plugin. So what happens is you write a ChatGPT prompt about data science, and if you create Python or whatever, you can see that code on the Notable website. And that way it will create whatever you want it to create. You don't have to cut and paste it. It's really very cool. And I've experimented with a great deal with classification and regression models. So I would say to those of you that have ChatGPT Plus already, you ought to try the Notable plugin and do a little bit of data science and see what you think. Okay, we'll go ahead and get started. Let me look at my list here. Where is our textbook? Our textbook is just about ready to go to the printer. The book designer is essentially finished with it. We're very happy with it. He was able to shrink it down from 506 pages to like 360 by going to 2 columns and intelligently posting the images. But we'll share some of that. But at this point, it's getting close. Let's put it that way. I want to spend 1 minute on self-publication. Somebody might say, well, why didn't you get Lippincott or Springer? First of all, they don't answer their emails. It's very tough to get hold of publishers. I've had a very bad experience, to be perfectly honest. I don't care whether it's asking them a question, sending them a book, or saying, hey, you have errors in your book. You need to fix them. You won't get a response, chances are. So self-publication, number one, you get most of the profit. It's true, you have to do the book designing, the marketing, the proofreading. That's the negative. But you get complete control and you get the vast majority of the profits. And most importantly, it's super current. When Lulu accepts the PDF that we're going to upload, within 7 to 10 days, we'll have the hard copy book in our mailbox at home for us to review. So that's the way to stay current. With a regular publisher, it might be a year delay between the time you give them what you think is your final draft and it's actually printed. So just a brief explanation of why we chose self-publication. I wanted to talk about one thing, and that is, it became apparent to Dave and I that we could create a data competition on Kaggle. And can you all see my desktop, by the way?
Yes.
Okay. Do you see employee attrition data set? This is on Kaggle. Notice it says the goal is to use orange data mining to explore the data, then create a classification model. What I did, I essentially cloned an existing Kaggle competition. So the guts of it are already done. How to submit, how to grade, all that content's already there. And so without going into too much detail, you can compete by creating your orange workflow, save it as a CSV, that your test results as a CSV, upload it to Kaggle, and you can be in the competition, not just for the one we created, but for any future ones. I don't know if there's any, but it's probably not worth our time if either you all are not interested or we contact the Orange folks and they feel they're not interested in playing or advertising on their website. Are there any comments back from you all about a data competition using Kaggle? If you want to unmute and just comment whether you think you're interested or not interested.
I think that would be interesting, but I don't know how to use it. So I will go today and see how does it work.
Okay. Well, again, at this point, it's just generating a CSV with the first column having the patient ID number, and the second column, in this case, attrition, yes or no, is the outcome. So what's going to happen is they're going to automatically grade. They know what a perfect score is, and they're just grading your CSV versus their CSV. So your test results versus their test results. So that makes it really simple. And in point of fact, you could compete now with any of the Kaggle competitions if that's the endpoint. If they say we want to see who generates the best F1 score, you could do that and then submit. But this is mull it over. Let us know what you think. But after looking at this in detail, we realize it's doable.
This is Brian. This is Brian. Bob since it's these are legacy prior competitions at Kaggle. Is it easy to see kind of the winner leaderboard in the live version of it to benchmark against, or is that going to be hard?
Yeah, and by the way, they're existing. I don't know what they call them, like demo. There's one about horse mortality outcome, believe it or not. You have to scroll around, just go to the competition menu on the left and scroll around, but there's some that you can practice, in other words, and yes, you can see where you are on the leaderboard. If you do super well, it's like silver versus bronze and whatnot. But the point is, they have a variety of competitions that you can play with, and they have some that you can clone. That's what I did. I simply cloned one. I changed the title a little bit, and we'll change some of the description and instructions. But we haven't decided whether to do it. If there's not enough interest, we won't do it. But it is doable, just based on the fact all you need is a CSV file. Okay, another thing. Anybody know what imposter syndrome is? I didn't know, but I think it's relevant to this field. Imposter syndrome is when you're in any kind of job where you feel overwhelmed and inadequate, that, oh my God, I don't think I'll, in any way possible, I can learn all this. Well, my only comment is I think for a lot of people in AI and even data science may feel that way until they get enough experience. And so I would say imposter syndrome is sort of the norm. If you don't feel it at all, perhaps you're a little cocky. So I'm just saying that imposter syndrome, I think, is very relevant to this field. So don't feel bad if some days you look in the mirror and say, I just don't know enough AI, let's say. We did put, by the way, a table of contents on our website, the nocodedatascience.net. If anybody wants to look at detail, table of contents, it's there. I did want to go over one thing, which is very simplistic, but that's okay. Let me see if it'll launch here. And this is just a short PowerPoint on, when we talk about no-code data science, we don't mean that you can skip steps. I mean, and it's really an advantage that you can get going really quickly with Orange, for instance, and that's what no-code data science is, mainly Orange and Jazz, versus programming. There's no question you can go from step 1 to step 2 much quicker without programming. But the other aspect of that is, though, when you actually look at pre-processing EDA, it doesn't make any difference whether you're programming or using Orange. You still have to go through all these steps. And so, you know, some of us would say that's no free lunch, if you will. I'm not sure. I'm seeing dictation at the bottom. I guess that's in PowerPoint. And then in modeling, the same thing. You can obviously do, say, logistic regression and immediately find out your sensitivity and specificity. But think about all the other things that you need to do. You're not done. It's a starting point. You know, you've gotten the first or second base. So this is just a reminder that we don't want people to skip steps, that this is can be somewhat of a laborious process. Let me see. Okay, let me get out of that. So I don't want to beat a dead horse, but to just comment that we really feel it's important that you all understand that. Now, the next thing is, I mentioned in the email that there's a new version of Orange, but also a new module called Fairness. It's going to be interesting, but it looks like they posted it somewhat prematurely. You can go in there and sort of measure bias and a few other things, but until Dave and I can really explore it further and run our own experiments to see how it influences the model. In other words, if you adjust the number of, say, women in a study, what happens? And we just have to explore it more. And I'm waiting on for them to add information to the widgets. In other words, if you right-click the widget, for most of them, there's no help menu, there's no information. So I think it would be premature for us to use the new module. So I'm not going to do that at this point. All right, so the next thing was in the homework assignment, and what I said was, and let me get stuff out of the way here, is that this homework assignment would be the really the last practice assignment in the chapter, where under the file menu, you went in and you used the Framingham heart data set. It's about 4,200 patients. There's some missing data. What's important about it, though, is it's imbalanced. And quick way to look at that is anytime you want to see a quantitative look at your outcome, which is predicting the 10-year likelihood of developing heart disease, again, and you want the actual numbers, box plot is great, where in the upper window you put 10-year coronary heart disease, the bottom the same, and here you go. So 644 versus 3596. I think that's 15% if I remember correctly. So you immediately know you got a problem. When you go over to test and score, what I want you to get in the habit of doing, remember to set the target to 1, is look at and say, AUC is not too bad, not great. The classification accuracy, wow, that's really good. Specificity, wow, that's really good. Recall, oh my God, that's horrible. And precision is bad, hence the F1 score, which is sort of the mean of these, is also poor. I can look at this in an article and I know right away I'm dealing with class imbalance. So the last, and I'm going to change the cross-validation to 10. You can play with it anytime you have a data set. If you have a small data set, and this is not a small data set, often you would go, you might go to cross-validation of 5 rather than 10. But what I'm trying to get you all in the habit, I guess it's still crunching numbers, is anytime you see that combination where the accuracy looks awfully good and the specificity is awfully good, but the rest is poor, you're dealing, in all likelihood, you're dealing with, let me try to close this.
Hey, Bob, while you're doing that, let me make a comment.
Yeah.
In his conversation I was having with Scott Campbell in the last few weeks about his data set. When we say here number of folds 10, so you're looking at 4,240 rows of data divided by 10. That's how many folds you have. If you happen to check leave one out version of cross validation, it's going to calculate 4,240 folds. That's obviously going to take a little bit more time. So if you click it on purpose or by accident and it puts you in a perpetual holding pattern, that's probably not a good option to use. You could maybe use it for really small data sets, but not for medium or large data sets.
Okay, yeah, that's an important point. Now, let me see. I hit escape to try to get rid of that table. Now I've got a black screen, so I'm not, let me hit escape again. I'm not sure what my choices are.
By the way, David, thank you for helping with me. My computer was running that program for like a week before I figured it out.
Yeah, right. Exactly. Yeah.
So I may have to quit Orange just in order to get a screen back. That's one of the pleasant things about having a course. Let me try. I'm going to have to go back and pull that up. But again, we're talking about imbalanced data sets, which are so common in medicine. It's rare that you would have equal numbers, say, of breast biopsies that showed cancer and ones that did not. So you need to recognize that and know how to deal with it. And let me just make one quick comment elsewhere. So as we mentioned before, weighting is probably the simplest and kind of the no-brainer thing. And I'm going to be going on how to shift the threshold in just a minute. Let me pull up recent here. Go back to the homework. So again, in here, we've done several different algorithms. Keep in mind, again, you always got the option of using ridge, regularization, and lasso. Again, what those do is they shrink down the predictors, basically, that aren't doing much. So it emphasizes the important ones and de-emphasizes the less important ones, and it gives you a better model with less overfitting, if you will. So again, let's look at a couple of things here. The receiver operator curve, and let me enlarge. I'm almost afraid to enlarge so it takes up the whole screen, then I don't know how to get rid of it. But as you can see, this horizontal line, 45 degrees, is the no talent zone. It's a wild guess, in other words. You want your curves to be in the upper left. Why? Because you want sensitivity to be up around 1, and you want the false positive rate to be down close to 0. So that's where a perfect curve would be way up there. These curves are pretty poor. I guess logistic regression ridge is the best. So that's just typical with imbalanced. Let's look at the performance curve. So this is precision recall. Normally, it's the mirror image of the receiver operator curve. And so here it's squished down, if you will. It's way down. It should be way up. And you're getting precision recall numbers of like 0.2, 0.3. So this is typical, but this is more accurate. So if you have imbalanced data, this is what you should be reporting and shooting for, the best possible area under the precision recall curve. So hopefully that makes it a little bit clearer. So let me go to the calibration plot, and we can look at, there's multiple curves you can look at. Here is an F1 curve, which is always, remember, F1 looks at precision and recall, which we're trying to improve. So you can adjust the threshold, which we'll show in a minute, by shifting that. When you shift it, you can see what the F1 does over here. Not too much difference, I suppose. Logistic regression, and I don't know whether that's ridge or lasso, is a little bit better. So you can shift that, but you can also look at all the other ones, precision and recall, and you can shift that this way. So you have to decide as a clinician what it is that you want. Are you happy with precision and recall, a compromise between F1 and with a compromise between precision and recall? How about sensitivity and specificity? You might shift it over a little bit closer this way where they intersect as an example. But let's look at a calibration curve. And again, it doesn't show up very well. Once again, you got that 45-degree. And down here close to zero, it's predicting close to zero pretty well, but is terrible up around 0.8 or 1. So it's not well calibrated at all. And then the confusion matrix, you can see that here, these are the true negatives, the true positives, false positives, 22. Look at the false negatives. So you really, a tremendous number of false negatives. David, other comments?
Yeah, just when you were doing the threshold shifting, I just want to make a comment that usually the default is 0.05, and Bob had already shown the optimal threshold at 0.2. And when your data is imbalanced, you have a lot of opportunity very often to shift that threshold to really get better performance on your models.
And then we'll talk about, I put a note over here that lo and behold, you can shift the threshold manually like this that I talked about, or you can calculate the geometric mean. So we'll go over that in a minute. I think we're ready, in fact, to start. Let me find, let's see, let me move this out of the way. Can you all see this okay?
Yes.
Yes.
Okay, good. All right, so where we were going to take, and we've already covered this to some degree, but it's nice to show you the orange and then talk about it and do both. In other words, remember that the receiver operator curve is always set, the threshold by default is 0.5. You can move it, as I've sort of already shown you. It's a movable object. And in fact, with class imbalance, it's much better to move it. You'll get much better results. So, and I'll show you evidence of that. So one way to do it is using those curves and shifting it and see what happens to, the F1 score, the area under the PRC, whatever. But you can actually calculate it by the geometric means. You multiply sensitivity times specificity, and you take the square root of that. That's pretty simple. And Yalden's J index is just a true positive rate minus the false positive rate. And then I've already shown you, you can calculate the F1 score at different thresholds by moving it. And again, you use the calibration plot widget under the metrics down drop-down menu. And this is just an example. This is using the stroke database, the stroke data set, which is really extreme, where you only have 5% strokes. So it means 95% don't have strokes. So if you use 0.5 is the threshold, notice that sensitivity of 0. It's basically not calculable. So if you start to decrease it, and I put 0.05, That's probably the best compromise, if you will, where sensitivity is acceptable, specificity is acceptable, not great. So this is a, excuse me, what you'll encounter sometimes. And you have to be aware that when you have severe imbalance, you're going to have results that are hard to interpret, and you need to apply these different methods to make some sense out of it, if you will. Now, I'm going to scroll down and go straight to the orange workflow. Now, okay, so you've shifted the threshold like I showed you in the calibration plot, as is here in this workflow. How do you save it? The answer is you just attach it to a save model. And what that'll do is it'll save it as a pickle file. A pickle file saves the whole deal. So not just your data, but it saves the Python model, the logistic regression, and whatnot. So it basically saves the workflow you see right here. And then you can upload that in this manner. You take, again, the file, the load model, which has logistic regression in it, but you connect it to predictions, not test and score. In the bottom of the predictions, it will have the outcome. It'll have accuracy. And I think what I showed, I don't know, again, where I can pull it up, but the F1 score improved considerably when that was done. The F1 score went from, I'm going to say 0.191 to 0.391. So there was an improvement. But the main point here is to get you to understand, if you manipulate the model in some way, be it in the calibration plot, you changed it, you can save it, but it will be saved as a pickle file. Probably something you've never heard about, but that's a Python function to save the model, and then you can upload it. But the thing that we say here is, in general, the easiest no-brainer thing is to use logistic regression, random forest, check the box inside the widget that says balance class distribution. That's not controversial. It's just giving more weight to the model for the minority class. So the model is not learning just on the majority class, it's learning on the minority class as well. Remember, that's the whole problem in machine learning. If it learns, it says, oh, wow, look, I have all these people who didn't have stroke. I'm going to memorize them and learn patterns on those people and not the people with strokes. That's bad. You don't want that. So again, it's important that class imbalance also worsens calibration of the model, because, again, it focuses on the majority class rather than the minority class. And so the calibration curve is likely to be off anytime you have class imbalance. And there are ways that you can try to, other ways that you can try to get your model to have better probabilities. And that is using the calibrated learner widget that has two different methods that you don't need to know the details of the difference between sigmoid and isotonic, but it's just another way that you can try to balance this model and get better results, at least partially better results. And in this case, in this particular workflow, I selected sigmoid scaling, and I wanted to optimize the F1 score, but it only does one classifier at a time, which is, unfortunate. But so you basically, as David has said many times, you should run a bunch, like 10 or 12 algorithms, find the best one, and then conceivably use that one at least with the calibrated learner and see if you get better results. Or you can do all of them. Dave, would you do all of them, all 12 with the calibrated learner, or just your top 3, let's say?
Yeah, what I typically do when I've tested this is when I go into test and score and I say, all right, I got let's say I got 1, 2, 3 algorithms that are great. What I'll do is I'll test the calibrated learner just in those top three, because it's not going to give them an incredible bump up in performance. It'll give it a little bit. So it's not like it'll take the least performing one and make it the best performing. So yeah, the top three is what you experiment with a calibrated learner typically.
Okay. And again, you may see improved results. This particular time, I think the results are underwhelming to go from 0.681 to 0.70. But again, depending on the data set and your circumstances, a lot of other things, which algorithm you chose, you might get far better results. Now,
just one more comment, Bob.
yeah, sure.
Sometimes it might not give you improved results. So there's no guarantee it'll always improve, but there is the chance it will improve.
So, and it all is about data experimentation, and I hopefully we've stressed that enough in multiple chapters that you always have to keep an open mind, and you can't assume that XGBoost is going to be best for everything. I mean, it's a great algorithm. Data competitors love it, but you'd be surprised in the long haul. You never know which one's going to perform best. And as I kind of indicated, so not just logistic regression, but logistic regression with no regularization, ridge regularization, and lasso regularization. So you might run all four. And that would be the more intellectually honest thing to do. All right, the next thing, so we've been talking about class imbalance, that your outcome of stroke versus no stroke. But what if in the stroke data set, you realize you only have 10% women? Clearly, the model is going to train and concentrate on men. So we're in the process, I think across the board, particularly in AI, of trying to figure out ways to balance that, to try to decrease the bias. I'm hoping this fairness new module may be a partial answer. I will tell you in that synthetic data program called Mostly AI, they now have an option in there to go in and literally balance almost anything, whether it's gender or the outcome or whatever. So you can do it. But I will comment that doesn't necessarily mean that you'll get better results in the model. What it may mean is that you get more appropriate results. Your relationships are more appropriate and more honest or more accurate. And so you get better correlations and ranks and whatnot. But the actual models say accuracy may not be any different. Scott, you had a question or comment?
Oh, yeah, really quickly. For feature imbalance, doesn't your data that you're using have to represent the community at large? And there may be imbalance within the community. So let's say, for example, 10% of my patients have chronic kidney disease. It's a really low number, but it does represent what's going on in the community. Or my community is 60-40 male to female. You don't necessarily go to 50-50, do you? Just because that's fair. Can you comment on that just to clarify?
Yeah, well, it's funny you mentioned that, because that was a conversation I started with David, and I don't know that we finished it, that I had the same concern of real bias versus non-real bias in that regard. David, you want to comment on that's a very important question.
Yes, great question, great topic. A lot of people are talking about it, and the issue is that whenever an algorithm sees that something doesn't have many rows of data that are attributed to that feature, it'll say, you know what, it's not that important. I'm going to focus on the most important stuff. So what you're trying to do in the background with these fairness and feature balances is you're not trying to necessarily always physically balance 50-50 for everything, even though that is an option and it is an experiment we want to do. But there are ways, and we're hoping that the fairness model will offer this for us, is behind the scenes, just shift some weights around so that the algorithms believe that each of the features that are underrepresented are actually as important as the ones that are overrepresented, so that they're not totally played down in the results.
But doesn't that undo the process of where we look at when we're exploring data in Orange at the very beginning, and we're ranking features so that we can remove some that aren't important in the initial correlations? Doesn't that kind of undo that? On one area, we're looking for things that are important, and the other area where, so we can take them out, the unimportant ones we can take out. In the other area, we're trying to balance everything. I think this is just a really important topic. We can't answer it here, but I'm confused a little bit about it. And then moving forward, I've seen panels where people have talked about certain features should never be included in a medical model. For example, some people were arguing race and sex because there's so much bias. So I just think it's a really important conversation to kind of push both sides and tell people we're working on that, but it's not necessarily everything being, quote, fair does not necessarily represent the best, what's going to be a good model. Anyway, thank you.
Sure.
Yeah, it is very important. And I think what we're trying to point out is that maybe a deficiency of machine learning is it doesn't learn equally if you've got class imbalance. And so we're trying to correct that. But again, the points that you raised are legitimate. And I think you're going to see more and more articles written, software developed and whatnot to try to get a better handle on this. Because certainly with AI, I'm not sure exactly what the answer is, because they trained on billions of parameters and information that may be biased, but how do you de-bias it is a whole different animal. So this paragraph here just emphasizes what we talked about, the fact that you need to adopt a highly disciplined and experimental approach in data science. Remember, chapter 2 shows you how to run a data science experiment. So you really are objectively evaluating a data set and not skipping steps, and also trying multiple different things with no assumptions, because you never know exactly what's going to come out of it. So now we're going to transition. Jason Brownlee, who's a well-respected computer scientist out of New Zealand who writes a whole lot, puts out a lot of, and I invite you to look at his books. They're ebooks, all of them, and you can bundle them and buy a bunch of them. But one of them he came out was imbalanced classification with Python. Now, the Python I wasn't too interested in necessarily, but the point was he mentioned a ton of different ways to handle imbalanced classification, and Dave's going to talk about that in a second. But leading up to that was a reminder, though, before you ever get to the balancing issue, you have to deal with missing data, outliers, scaling, meaning what happens if in medicine you've got blood pressure at one scale and, say, a SED rate at another one. So scaling means applying normalization or standardization. And multicollinearity, we talked about a great deal. So David, I'll turn the floor over to you for number 2.13.
Sure. Let me get it set up here. Do my screen sharing.
Let me stop just so you have it.
Okay, I hope everybody can see the screen now.
Yes, I can.
Good. So, model selection criteria. We have a situation here where that if you search the internet for, let's stick with classification models because they're so common in healthcare and in medicine. If you search all the metrics that are there, you'll find that there's about 26 of them. You say, oh my gosh, 26. And how many does Orange offer? Well, if you remember, if you go into the test and score widget in Orange, and I'm just pulling it up right now. I hope you could see it. I just popped up orange test and score widget, you could see that there's not a whole lot of them that are actually there. And, you know, so are those the most important of the 26 that are actually available? Well, you know, that's a question, and that we'll talk about this a little bit. But, you know, the whole issue is we have this conflicting priority that, you know, I guess we could call multiple metric mania, or that, you know, do I really got to look at all 26 of them, or what in the world do I do, you know? And so which of these metrics are important? And when you're teaching somebody about machine learning, that's the most important thing that, and then the most confusing thing for them to try to appreciate in the beginning is what metric or metrics should I actually be looking at? Can I really just focus on one? Can I focus on multiple, or what do I do? You go into a Kaggle competition, it's pretty easy because they'll say, hey, you know, the winner is going to be the best F1 score or some other type of metric. They'll tell you right away and say, you know, optimize your model, everything you could do toward this one metric, and basically forget everything else because you're not going to be in the leaderboard if you got a great different metric, but you don't have this one. So as a clinician or professional in whatever different industry, it's really important from the very beginning that you determine what is your most important metric for you. Are you more interested on precision or recall? And you could see here, you know, we have F1s and F.5s and F2 scores. You know, the F1 score is what is readily available and calculated in orange, and you look at the other like F2 and F5 scores, 0.5 scores, and what those are typically doing, like the F2 score, puts a lot more focus on recall, and then the other one, the 0.5, puts a lot more focus on precision. So it all depends of the problem you're solving or the predictive model you're trying to do. What is the most important for you? And then we get into other types of metrics like Breyer scores, and you know, like again, we could get into this whole multiple metric mania, and as fast as I could rattle off their definitions of each of them, you would forget them because it wouldn't expect you to fully understand and appreciate all of them. So, and this is a modified chart that we have from Brownlee, you know, especially let's look at imbalanced data. You know, what do? How do you predict the classes? And do you do weighting and predicted probabilities? And then the whole question of, you know, what metrics do you start to look at and everything? That gets into a very complicated type of situation. But the bottom line is, you know, are you more interested in being, you know, looking at precision or recall? Do you want to focus on getting false positives down or false negatives down? And then you have to then, based on those conversations with yourself or other experts, you then make the decision of what is the correct metric for you. And then if you got imbalanced data, you got this whole other situation to deal with because that's going to skew all the metrics off into the twilight zone. And like Bob was showing earlier, you get some that are either non-calculatable or are just outright zero. And it's not because there's something wrong with that metric, it's because the data was imbalanced. So there you see in this bubble we have here of weighting, we at least have a few of the algorithms in orange that could automatically add the weights and balance that, you know, to give it a fair shot. And then there's also this model, this method of balancing, which is called SMOTE. And, you know, Bob and I have created our own SMOTE widget within Orange, but it's not available within the Orange, you know, software. It's something that we created on the side. And and then there's the whole topic of undersampling and oversampling to help deal with imbalanced data. And again, why do we even bother to deal with imbalanced data? Because it just totally messes up a lot of our metrics. So we got to, and it makes it difficult for us to figure out which algorithm is the best. So that's why we like to lean on these other methods of, weighting, automatic weighting, at least for the logistic regression and random forest, which Orange offers, and also the under and or oversampling of the data to at least, again, you only do that on your training data set, not on your test data set. And then that'll help you give all the metrics a fair shot at telling you what they should really be calculating if everything else is considered equal.
Dave, I think Scott Campbell had a question or a comment.
Oh, just a quick question to you and to the group. Do you think that the FDA has any understanding of what you just spoke about?
Oh, I am 100% sure that they have data scientists that understand everything that I said and could add, another hour dissertation to the whole thing. But whether those people actually have any say in the policies and everything within the FDA, I really cannot answer that.
Right, because with the commercialization flood of these products, it's very difficult to understand any number of things of how they were trained, et cetera, what metrics, et cetera. So I just think it's a cautionary tale for those that are looking at build versus buy.
Yeah, and Scott, to that point, I would say it's a bigger problem with actually journals. The editorial staff doesn't seem ready to deal with this either, where there's really not a checklist for machine learning articles being submitted where they say you must report the following. All too often, there's cherry picking where they'll report accuracy, fully knowing that it's not a good thing to report if you got class imbalance. And there's nobody there that makes them go back and redo it. Only a few editors or journals require the confusion matrix to be posted. So I would say lack of quality in the journals may be the biggest issue right now.
And I put a link. There is a group, SENDAC at North Carolina, that proposed that we should have a food labeling approach to articles. There's a really great chart if anyone wants to look at that. And I think at least that's a start for some consistency from journal perspectives and from model building. It has to have X, Y, and Z, or this is what it doesn't have. Use at your own, use with your own caution.
Okay, Scott, this is not the article on labeling algorithms that way. That's another article, right?
No, that's that article. I'm sorry, that is that article around how we need consistency in algorithm analysis. That's all.
Okay, all right. Well, I'm familiar. That is, I think that is a good article. Thank you for posting that.
Now, what Bob and I were scratching our heads on this, I think it was the beginning of early last summer, very, very feverishly trying to look at this whole metric situation. So I might have you in a depressing hole right now, but I'm going to get you out of that hole pretty quickly, hopefully with some solutions. But if you first analyze a lot of these famous metrics, not all of them, but most of them are all calculated from the 4 elements that you find in the confusion matrix: true negative, true positive, false negative, false positive. If you look at this, and I hope you can see right now, I have an Excel document pulled up, and you could see here all the different names for all the different metrics, model metrics, and not even all of them use all 4 of the elements that are available in the confusion matrix. And you can see wherever there's a yellow square, like, recall, that uses, well, true positive, false negatives. And then, specificity, what's that do? Well, it uses false positive, true negatives. And you can see only when you get toward the bottom do you find some metrics that actually use all 4 of those elements coming out of the confusion matrix. Now, just because you use all 4 of them doesn't necessarily mean, oh, wow, that's a perfect metric, but it does give you a higher chance that those metrics are actually better and more worthwhile to focus on. As an example, look over here. Is that metric robust for imbalanced data? Well, one of them is, a lot of them are no. And then toward the bottom where, you see a lot of these metrics are using all four elements of the confusion matrix, a lot of them are yes, but again, some of them are no. So how do you get around that whole thing? So again, we were experimenting last summer with this and was playing around with a scorecard. And since all of these metrics are based on, the four elements of the confusion matrix, the TP, TN, FP, FN, I've set up here a spreadsheet where that they could automatically be calculated and compared on a certain model, which algorithm is best. But again, here's where you get some confusion. Like one time you might have recall is best, but then specificity is not really best. So which algorithm is really best based on these metrics? Sometimes you could get some really conflicting metric scorecards. And what I was experimenting with, and if you look to the far right, you notice something Bob and I haven't got around to publishing yet because we were working on the book. But we came up with something that we call, a little bit, all these metrics have names. Cohen's Kappa. Well, guess what? Cohen is a name of a person. And Folks Mellows. Well, guess what? Those are name of two people. So following that scheme, we came up with something called the Patrishkov-Hoyt score. And like it or not, that's the way we call it, PHS for shortcut. And just as an experiment, what we did is took all of these 16 different metrics that are easily calculatable from the four elements of the confusion matrix and looked at, all right, what happens if we do a sum of them all? What happens if we do a average of them all? What happens if we do a geometric mean of them all? And what we're trying to come up with is one kind of surrogate metric that you could look at and say, oh my gosh, what do I do with this multiple metric mania? How do I deal with it? What we're trying to come up with is one composite metric that would factor in all of the essence of all of these, the good and the bad and the ugly, so to say, of each of these metrics, and either add or average them together and try to use that as the discerning one metric that tells you which algorithm in your model is the best. And that's what we're experimenting with. We need to do a lot more experiments before we could actually say that's the way to go and do a publication on that. But we're pretty certain that that's the way to go do a composite metric on that.
And Dave, just a comment, that's actually the first time I've seen that table, that Excel spreadsheet. I'm going to say, why don't we post that under resources on our website?
Sure.
That's a great table. And I can't emphasize enough how important it is as a clinician, to understand that basic stuff of things like sensitivity and specificity. There's one in there, by the way, that we never talk about, balanced accuracy. It's just sensitivity plus specificity divided by 2. The idea being, in an imbalanced data set, your sensitivity is falsely low, your specificity is falsely high, so you just average it. So that gives you one other parameter, and that's an easy one. But I think that table is something I sure hope you spend some time on, and I will try to today post that on the website.
Sure. Now we get into another topic that can be incredibly complicated: hyperparameter optimization. What in the world is that? Well, when you've finished doing your model and you finally figure out, okay, what's your main metric, and you think you know what the best algorithm is. What do? Do you just run to the bank and start forecasting, telling everybody we should be doing this, we should be doing that? Or are there other ways to optimize the model? One of the ways Bob already talked about a little bit, threshold shifting, is one way to optimize a model. Hyperparameter optimization is another way to optimize a model. Now, what in the world is hyperparameter optimization? For that, I'm going to pull over an Orange workflow, and almost every one except one of the algorithms, and this is showing all 23 that I like to use when I'm doing some very serious stuff. And they have all hyperparameter optimization tuning. And we have a chart that will show up in the book, but I wanted to show you, let's just click on logistic regression. And so what are my tuning features that I have? Well, you could see here my options are I could select either lasso, ridge, or none. And then I have the regularization strength. I could bring it all the way to the left, leave it in the middle, make it to the right. So that's a tuning factor. And sometimes if I'm really interested in finding the absolute best model, I might break this up into 5 different levels and experiment with 5 different levels of regularization. Then I have this on-off button, whether I can balance the data or not. And these are considered hyperparameter tuning features. Each of these algorithms has a different set. Let's say on the tree, these are all different, these are all options under the hood that you could tweak on the engine with your screwdriver, so to say, make this value a little higher, this value a little bit lower. And then you have to set up a very detailed experiment to see which one of these actually help and which ones don't help. And to make it more complicated is it's not like you could say, oh, well, okay, here's the default settings, or let's say I came up with some other settings, and this is always going to be the best for every data set I have. Unfortunately, that is almost never true. You have to do this optimization just like you have to do for the threshold shifting. You have to do that for every individual data set because the nuances of that data will force you to start from scratch. And you see, I could go in here and I don't want to do it now because it'll mess up the whole model and recalculate everything from scratch. But I could pick any different type of number on these 4 different hyperparameter tuning features for the tree model. If I go under K nearest neighbor, you could see I have other types of options. I could say the number of neighbors and so on and so forth. But I think you get the point. You could double click on any one of these algorithms, except for naive Bayes. And you can see here, there is nothing to tune. But everything else, you have an option to tune. And what that is that's basically a call for you and a challenge for you to do an experiment to see if you could then beat your model's performance based on the metric that you selected as the best to actually perform better. And you won't know until you actually try it. Now, we don't have within Orange, we don't have automatic ways for us to actually, just tell Orange, hey, can you do all this tedious hyperparameter tuning stuff for me and just experiment and I'll walk away for a few hours and then you tell me the response. We don't have something like that or a widget for that in Orange. There are some opportunities within Python to do that. And some of those methods are called, you can see here, are called grid search, and some of them are called random search. So what's the difference between the two? Well, let's see if I got 4 different parameters that I want to tune. If I were using grid search, I would say, you know what, I'm just going to increase each one of them by 20%, and I'm going to make 4 different settings that I'm going to use, and I'm going to run the experiment. That would be like a grid search. So there would be like a mathematical difference between each of the settings. Now, random search is a little bit different. It actually looks at all the settings you want to try on one matrix, on let's say the x-axis in a spreadsheet, and in a y-axis on the spreadsheet it has some other ones, but it's going to pick random numbers that separate the settings from each other, and not just like I said, 10% or 20% difference. So those are 2 different methods, and you could read about those in the literature. Sometimes, depending on the data set, the grid search is better. Sometimes the random search is better. But the point is, to get to the bottom of that, you really have to do experimentation. And if you go down to this, we have in our book, we have this, let me make it a little bit smaller so I could get the whole thing at least fitting into one screen here. We have here, we could see these are all the hyperparameter tuning options. They're listed down over here, down this area. And then you can see all the main, let's say the main 11 algorithms that you could tweak are up on top. And then whether that option is available within that algorithm is shown with a yellow square. And you can see that a lot of them at the very top, actually, you'd say, oh, wow, they have the same type of algorithm. Well, that's only because they're all within the logistic regression family, regularization rate and those types of things. So again, you got to first of all find out what's your best algorithm. And then based on that best algorithm, and let's say, for example, your best algorithm is random forest, then you say to yourself, okay, can I squeeze a little bit more of an improved F1 score or whatever your metric is out of that random forest algorithm? And then for that, you would want to go in here and then play and experiment with these different types of parameters to see if you can get a little bit of a better F1 score, in addition to other things you might be trying, balancing the data, and like we already mentioned before, threshold shifting. So if you're really trying to improve a model, not just create a model and squeeze everything you can out of it, this is what hyperparameter tuning is all about. And if you go to in blue sky statistics, which we don't cover a whole lot in our book, we talk about it and talk about its features, but we don't give too many examples because of if you compare, for example, JASP and orange and blue sky, orange we believe is the best way to go, because for a lot of different reasons. It's not that difficult. And once you set up a workflow, your workflow is set up. You could use that for all different data sets. JASP supplements orange, and blue sky is a little bit more difficult to use than orange. And it has this rather annoying feature about it. And it's not because blue sky is bad. It's because there's some limitations within R. For example, I could go into orange and I could put all these, I like to call them horses in the race. These are all 23 different algorithm options. And whatever data set I have, I'll let them all compete against each other, and I'll see who's the winner in the test and score widget. I might have to walk away from my computer for 45 minutes or maybe 2 hours, depending on the size of the data set. But when I come back, I will know how this horse race ended. I can't do that in R, which means I can't do that in blue sky. I get to test every one of these individually, copy and paste those results somewhere in the scorecard outside of the software, and then compare that. So that's a rather annoying feature that is kind of adds a lot more work to getting to the bottom line of what's really going on. And that's another one of the reasons why we really like, one of the many reasons why we like orange. So,
Dave, Scott had another question or comment.
Very quickly, to David and Robert or anybody in the group, I'm thinking of all this in the context of a federated learning model. And if I've got 5 hospitals trying to train a clinical decision score with their data, there's agreement about what model people are using. But I'm starting to think, should we allow them to train that model, and everybody keeps the hyperparameters the same, and then they send the model to the federation? Or do you sort of allow them to, have the horse race, build the best you can on that iteration, and then move the model and its weights to the federation? So I don't have an answer to that, and I don't know that the federated learning people do too, but this is an important aspect, I think, of collaborative learning.
Yeah, my comment on that would be is if you're talking multiple hospitals, you're probably talking multiple data sets. And if you're talking multiple data sets from different hospitals, the chances of the same algorithm creating the best model for all the different data sets is pretty rare. So
Well,
that's
it can be. That's not necessarily true if you have multiple hospitals within the same closed system on the same EMR. For example, everybody at Mayo. So anyway, that's an esoteric point, but I think you get a little bit away with that when you use it within a closed system and insist on consistency about how the data is collected. But anyway, thanks.
Yeah, if they're using the same data set, then you could forget about what I just said. But my comment was only reserved to if they're only worried about predicting the data from the people in their hospital and ignore the electronic health record information from people from other hospitals, then that's going to be an issue.
Yeah, and I think the federated learning model was, in a way, designed for disparate institutions. It would be easy if it was all done in one system, but I think they're talking about disparate ones. And the problem is they also have to have unbelievably good data governance with a common data model. So you have to use the same abbreviations. There are a lot of obstacles, as you can well imagine, trying to get everybody on the same page. Physicians and hospitals are notoriously independent. So again, enough about that, but it is a challenge to try to get these models and their weights uploaded in order to compare apples and apples. So Dave, you got one more section, and I think we won't move to chapter 5. We'll finish with 4.7.4.
Right. So here we are avoiding model fitting. We're going to talk about here. And model overfitting is, a very important aspect of modeling. And what overfitting really is, at its essence, is you have an algorithm or a model that's basically doing a great job of forecasting and predicting all the noise, but it's not really doing a good job of forecasting the underlying pattern and signal. And when that happens, then it really doesn't do very well on new data it hasn't seen yet, new patients or new whatever you're trying to forecast. So there's interesting ways how to generally deal with addressing this, reducing overfitting. And we have the cross validation. We've talked about that several times. There's different ways of setting it up with 5 folds or 10 folds. You could even go as high as 20 folds. And like Scott knows, you could even do, the leave one out, and then you'll have as many folds as you do rows of data. But you want to have a powerful computer if you do that, because it's going to take a very long time to calculate. But the regularization options within Orange for specific algorithms, the regression algorithms or the neural network, they're available, and they do a really nice job of toning down the overfitting. But again, regularization is not always a hyperparameter option available for every one of the algorithms. And then you got, feature selection. You got to watch out that selecting only the highest ranked variables in a model. You got to watch out if you have high variance inflation factors, which can mess up and create overfitting. There's also there's an option of early stopping. For example, if you let a model just keep on spending an infinite amount of time doing, calculating, it's going to overfit the model too. And then, but there's ways to get around it. It's called early stopping. And then training on more training data can help us reduce overfitting. So in general, those are some of the ways that can help you get around overfitting. And I think what I'll do right now is stop, and we'll open it up to any questions or comments that anybody might have.
Yeah, feel free to unmute and ask any questions that you have. I don't think, again, we'll move on to chapter 5. We're sort of out of time, but I will be sending chapter 5, the new chapter 5, to you all via email. The next class is November the 11th. just so you know, and I will add some content to the resource section. You all should look there anyway, just to see if there's stuff there that's of interest to you. Any questions though about imbalanced data? Since that's sort of the thrust of what we've gone over the last 2 months. Okay, just, so the take-home message is be always aware that may be an issue with your data, and be aware of the different techniques to deal with it. If there are no comments, questions, or concerns, I'll probably go ahead and end this one. Of course, we'll post it on the website. Let's see what, Kelly, you were see in the future, will we register for these Zoom sessions or move forward receiving a Zoom link? You'll get a Zoom link. So, we'll send it out that way for sure. So I'm pretty sure you're on the mass email list. And I appreciate you all attending today. You all are some of the most reliable, loyal people we've seen, because I see your names almost every single month. So we thank you for that. You've given us very valuable feedback. So if there's no other concerns or comments or questions, I'm going to go ahead and end the recording. Dave, if you want to hit the stop record, and then we'll go ahead and end this section, or session,
Right.
rather.
Okay, everybody.
See you next
See you next time.
Okay, bye-bye.
Bye.